In Section 9 notes, we are going to talk about scientific notation. In the Base 10 ALICE activity, we were looking at how we could utilize scientific notation to express how tall Alice is after eating Base 10 cake. So if Alice is 4.5 feet tall, we can multiply her height times the type of cake and the number of ounces. So 4.5 feet times 10 to the ninth is what Alice's height would be multiplied by if she had 9 ounces of base 10 cake. So how big is that? Well, if we took the number 4.5 and we moved the decimal place, as multiplying by 10 to the ninth is changing the place value 9 places to the right, hundreds, thousands, millions, billions, 4,500,000,000 times as big, that's a giant number. This 4.5 times 10 to the ninth is that number in scientific notation. So what are the rules for scientific notation? Well, it is, first of all, what is it? It's a way to write really small or really large numbers where the coefficient is multiplied by a power of 10. So the coefficient up here in this example is 4.5 times 10 to the ninth. So the coefficient out front can be positive, negative, between 1 and 10. And the power is times 10 to something, whether that exponent can be positive or negative. So here are two examples. 45,030. If we were, the decimal place is over here on the right side, move that over until it is between 4 and 5. We have times 10 to the fourth, the positive exponent. If the number starts super small, as this one, we would need to move that decimal place over to the right in between the 7 and the 6, resulting in 7.6 times 10 to the negative fifth. So we're going to go through some examples converting back and forth between standard form and scientific notation. So these three numbers here are in standard form. We're going to write them in scientific notation. And so to do that, we need to know where is our decimal place starting. So this number here started, the decimal when it's not there, obviously is over here on the right. And so if you've worked with scientific notation before, you've possibly seen someone draw kind of some humps in between until you realize where you need to stop your decimal place. So if I'm counting as I'm drawing my, moving my decimal place over, it's 1, 2, 3, 4, 5 places. So we're going to have 3.4 times 10 to the fifth. Same idea here. We have a number that is too small to be in scientific notation. We need that coefficient to be between 1 and 10. So we're going to move this decimal place to the right 1, 2, 3 spots. And so we're going to have 5.12 times 10 to the negative third. And the last example here, this is a very large number, decimal place over here all the way on the right. We're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9 spots. Excuse my sloppy handwriting here. And we do have to write everything after the decimal place until everything's only zeros. So in this case here, we did have to add the numbers a little bit longer, 9.007 times 10 to the ninth. So the next example here, we're going backwards from scientific notation to standard form. So these numbers out front are in between 1 and 10. So again, if we have a positive exponent, we know we need this number to get bigger. So we're going to move our decimal place over to the right 5 spots. 1, 2, 3, 4, 5. And every place where there wasn't a number, you know that you would fill that with zeros. And so our answer here, after 4.2, you would need 1, 2, 3, 4 zeros, and resulting in 420,000. If your value is times tend to a negative exponent, we know we need this to get smaller. So we're going to move our decimal place to the left. 1, 2, 3, 4 spots. And then in front there, we would have 1, 2, 3 zeros in front of the whole number here that was given as our coefficient. And of course, on example C, another example where it's a positive exponent. So we're going to take that decimal where it's at, we're going to move it 7 places to the right. The exponent does not dictate the number of zeros in the problem. Okay, it is the number of decimal places you need, or place value, okay, the number of places we need to move. So if we move that decimal place 7 places, we're not adding 7 zeros, we're not adding 6 zeros all the time. It depends on what the original number format is. 1, 2, 3, 4, 5, 6, 7. So how many of those place value spots don't have values? 1, 2, 3, 4 spots that would need zeros behind it. So that is the instruction that you need for going back and forth between standard form and scientific notation. And what I'd like you to do here is hit pause and try these 3 examples to remind you of how we can simplify problems with exponents. Notice that none of these are in scientific notation. This is a general reminder of how we work with numbers that are multiplied together, two values being divided, and power to power. When you're done trying A, B, and C, hit play. Okay, so hopefully you had some time there to check these out and try them. And notice that 5 and 6, those are coefficients. 5 times 6 is 30. We have x to the 8th and x to the 7th, two bases that are the same. 8 plus 7 is 15. On example B, we have 30x to the 9th divided by 15x to the 3rd. 30 and 15, those are coefficients. This is a division problem. 30 divided by 15 is 2. We have x to the 9th and x to the 3rd. Remember, that's like cake and beverage. They're going to cancel each other out. 9 minus 3 is 6. All of that would end up in the numerator of the problem. And on 2x to the 5th to the 3rd power, remember this is 2 to the 1st. This 3rd power needs to get applied to everything as the base. So we're going to get 1 times 3 and 5 times 3. So we're going to get 2 to the 3rd, x to the 15th. If you were asked to evaluate, 2 to the 3rd is 8. So in general, if you are asked to simplify problems in scientific notation, we can simplify with those exponent rules that we just practiced. We're going to multiply and divide coefficients, and we're going to add and subtract powers, or use our power to power multiply. Once you have multiplied or divided those coefficients, we need to double check that the coefficient is still in between 1 and 10. If not, we can then convert to proper scientific notation and just adjust the exponent as necessary. So looking forth here to example 5, we have 3 times 10 to the 8th times 2 times 10 to the 7th. So just so you are aware, like you can have a scientific notation problem with the old-fashioned times sign. You could also have some examples like here on D, we have 2 times 10 to the 4th. You could have just the dot representing scientific notation as well. So example D and example A are representing the same thing. We have 2 numbers in scientific notation being multiplied together, and they're in the middle. So those coefficients that we're going to look at are 3 and 2. 3 times 2 is 6. 10 to the 8th and 10 to the 7th, those are the same bases, right? So we have 8 ounces of base 10, 7 ounces of base 10, so we have a total of 15 ounces of base 10. Now, we've multiplied these together. 6 is in between 1 and 10, so we know that that is our final answer, and we do not have to do anything further to finish that problem. looking at example B, we have 36 times 10 to the 8th and 12 all divided by 12 times 10 to the 6th. Again, 36 and 12, those are your coefficients out front. 36 divided by 12 is 3. And 10 to the 8th and 10 to the 6th, those are the same bases, so we can remember we have cake and beverage. They will contradict each other or cancel each other out, leaving you with 2 as your exponent once you subtract 8 minus 6. And the third example here is 3 times 10 to the 5th all to the 4th power. So this 3 has a 3 to the 1st. We need to apply the power of 4 to that 1 and the 5. So remember, power to power multiply. So we're going to end up here, or start with, I should say, 3 to the 4th times 10. And I have a typo there. 5 times 4 is actually 20. And then if you were to finish that out, 3 to the 4th off of your exponent sheet, you're going to see is 81. And so I'm going to update that to our 20 as well. But 81 is not in between 1 and 10. So we need to move our decimal place over to the left. And so that's 1 spot. So we need to add 1 to that exponent that we already had there. So we're going to have 8.1 times 10 to the 21, or 21st power. Okay, so that is 3 examples there in scientific notation where you are using the rules that we have learned already. There are, I believe, 6 more examples left here. Yeah, D, E, and F, and G, H, I. So at this point, if you're feeling super confident, go ahead and hit pause, try the last 6, and hit play. If you would like to see how to work out 3 more before you hit pause and try the last 3 on your own, do as you see fit to gain the knowledge that you need in this video. So on example G, here we have 12 times 10 to the 8th and 3 times 10 to the 3rd. Those 2 expressions are being divided. So 12 divided by 3 is 4. 10 to the 8th and 10 to the 3rd, those are going to cancel against each other, leaving us with 10 to the 5th. 4 is in between 1 and 10, so we are done with that problem. On H, what would be good for you to realize here that if this problem starts with this old school division sign, I would recommend writing your 2 expressions, 15 times 10 to the 9th divided by 3 times 10 to the 3rd, as a fraction, so you can realize what do you really need to do here. 15 divided by 3 is 5, and 10 to the 9th and 10 to the 3rd, you're going to subtract 9 minus 3 and get 6. Another example here on I, we have 8 times 10 to the 5th, all to the 2nd power. So remember, 8 to the 1st needs to have that 2nd power of 2 distributed to it. So we're going to have 8 squared times 10 to the 10th. And 8 squared is 64, which is not in between 1 and 10. So we would need to move that decimal place over from behind the 4 in between the 6 and the 4, so that's 1 spot. And we would need to adjust our exponent and make it 1 bigger. And so we're going to get 6.4 times 10 to the 11th. Again, if you haven't tried those examples on your own yet, you can hit pause and try D, E, and F. I'm not quite sure why I accidentally skipped ahead to G, H, and I. If you were expecting to see those in order, I apologize. But here we go with example D. So 2 times 10 to the 4th times 4 times 10 to the 3rd. Your coefficients are 2 and 4. Excuse me. 2 times 4 is 8, and 10 to the 4th and 10 to the 3rd is going to result in 10 to the 7th. On E, 5 times 3 is 15. 10 to the 4th and 10 to the 3rd would get added together and have an answer there of 10 to the 7th. Seeing here that 15 is not in between 1 and 10, we would need to move our decimal place over one spot there. And so we are going to get 1.5 times 10 to the 8th power. I'll get this on here and adjust it a little bit. There we go. And on our last example, example F, we have 12 times 10 to the 4th times 2 times 10 to the 8th. The coefficients there, 12 and 2, are going to get multiplied together. 12 times 2 is 24. Same base add there. The 4 plus the 8 is 12. Again, this is a problem where we are not in between 1 and 10. So we would move that decimal place over between the 2 and the 4, and so we would need to add 1 to our exponent, and so we're going to get 2.4 times 10 to the 13th. So again, sorry for skipping ahead and doing examples G, H, and I before the others, but that should be a good start for you so that you can now practice those scientific notation problems on your own.